Welcome everyone to another video on limits. I have made two videos for this section. The first part is we'll talk about the limit laws and then we'll use direct substitution method to find the limit. And in the second part of the video, we'll talk more about the rational functions and then we'll talk about evaluating limits of rational functions by factoring and rationalizing. So before we proceed, we have few limit laws here that we need to discuss and we'll use here. So if we have two functions such that the limit as x approaches a of f of x, this function, and then there's another function that the limit of that function also exists. So both those limits exist. And then we have a constant c, then the following statements are true. The first one says the limit of um, the sum of two functions equals to the sum of their limits, or the limit of difference of two functions equals to the difference of their limit. And this law is called sum and difference law. Sum and difference law. Then we have another law which says that the limit of the product of a constant and a function. So if we have a constant in front of the function and we are evaluating the limit, it is okay to factor that constant out and then evaluate the limit and then multiply. So this law is called constant multiple law. So we are multiplying by a constant. So if we have a constant, then it's okay to factor it out, evaluate the limit, and then put it back. The next one is called the product law, which states that the limit of product of two functions equals to the product of their limit. Okay, and the next one is called the quotient law, where we have limit as x approaches a of quotient of two functions f of x and g of x, then that equals to the limit of f of x divided by limit of g of x. That means we can distribute that limit as long as the denominator is not equal to 0. So if this denominator equals 0, then of course this would be, that expression would be undefined, so we cannot have 0 in the denominator. The next law that we have is called the power law. So this is called the power law. And then this states that limit as x approaches a, f of x raised to the nth power equals, so we can evaluate the limit first and take the power. Okay, so here we have the limit outside, but we can put this inside and then evaluate the limit and take the power. That is called the power law. And the last one that we have here is called the root law. So we are dealing with the function with root. So this is called the root law, which states that, so if we have limit x approaches a of nth root of f of x, then it's okay to put this limit inside. Okay, so we can put that limit inside, evaluate the limit, and take the root. As long as, so there's a restriction here. Okay, this is true. Okay, if it is, or if n is odd, then we don't have to worry because we can find the odd root of positive or negative number. So there's no restriction if n is odd. But if n is even, then we must have this quantity inside the square root be non-negative. So if we have a negative number inside this square root, inside that even root, then that's not valid. I mean, we cannot evaluate that. Okay, so if n is even, if we have the square root, or if we have the fourth root, or if we have the sixth root, so if these numbers are even numbers, then we must have this quantity greater than or equals to 0. Means it should not be a negative number. Okay, but if it is odd, then it's okay to have negative or positive numbers. So when you are dealing with that square root, we really have to be a little bit careful. If we get a negative number, then we cannot do that. Okay, so those were the limit laws. Now we have two special limit or two special functions whose limits are known just from the graph. and then we can use this one to extend the concept. Okay, so the first one says if we have a constant function, and you know that the graph of a constant function is just a horizontal line. So if I draw the graph of a constant function, so f of x equals c, that means the y value is always constant. Okay, so if we have that, then so for example, if I take a somewhere here, it doesn't matter what a I take. So when we approach to that a from left and right, we approach to this point, and if you have a point on that graph, that means the value of the function is always c. That means the limit is always going to be c. No matter what a we choose, the limit is always c. That is why if we have a constant function, or if we have a constant, then the limit of constant is always that constant. The first one. The next special function that we have over here is the identity function. So identity function means the graph of identity function looks like this. So let me draw it here. So the graph of identity function looks like this, which is y equals x, or f of x equals x. So this is our function here, x. That means the value of the function is same as the value of x, or the input and output are always same. That's why it's called an identity function. Now this is what happens if I choose a here. So as x approaches a, the value of the function approaches to this point here. And then we know that y equals x. That means if I choose x as a, y is also always going to be a. Okay, so whatever x I choose, that is the value of y for the identity function. That means as x approaches a, y approaches a. Okay, so that's why the limit of an identity function, or limit of x as x approaches a, is just a. So now these two special function or special limit are so special that now we can use this one and the limit laws to extend this to evaluate limit of any functions. Okay, now we have this power function here, which is this is very important. We can get this one by using the limit law 5. So if you remember in limit law 5, we had this. So limit as x approaches a of f of x raised to the nth power equals limit as x approaches a f of x, and then we take the nth power of the whole thing. So now if we use this law and this second limit here, okay, then we'll get this formula right here. So this is how we get this. So limit x approaches a of x to the nth equals, now if we use the limit law right here, then this can be written as limit x approaches a of x to the nth power. Now if we use this limit number 2 here, then that becomes a limit as x approaches a of x is just a. So that becomes a to the nth power. So that's how we get that formula. Now see, if we have x to the some power, then we can just find the limit by substituting x with a. So it's super easy. Now if you have, what's the limit of x approaches 5 of x squared, then what you can do now is you can just substitute x with 5. So 5 squared, which is 25. Okay, so this law makes the work of finding that limit so easy. Now you don't have to draw a graph of that function. You don't have to make a table. Simply, if it's a power function, you can just substitute x with a and evaluate the limit. So let's look at some more examples here. So the first example is we are going to evaluate this limit using limit law, okay, and then see what we get. So the first example, so the first law that we are going to use is the quotient law. That means I'm going to put that limit. So let me start writing from here. Okay, so I'm going to put that limit to the numerator and denominator. So I'm going to use the quotient law. Now when you're using quotient law, one thing that is very important is you have to check. If you get a 0 in the denominator, you cannot use the quotient law. So I'm going to check that. So if I put 3 here, 2 times 3, 6 minus 5 is 1. So it's not 0. That means I can use the quotient law and rewrite this as limit x approaches 3 of square root of x cubed plus 2x minus 8 divided by limit as x approaches 3 of 2x minus 5. Now for the numerator, I can use the root law. So I can put that inside the root. So as long as it's not negative and we are not going to get negative, we'll check that, okay? But let me put it in. So we can put that inside the root. So square root of limit x approaches 3. So this was the quotient, sorry, quotient law, okay? And then here I'm using the root law. So x cubed plus 2x minus 8. And then in the denominator, I can use difference, sum or difference law. So that means I can distribute that between these two. So I can write limit x approaches 3 of 2x minus limit x approaches 3 of 5. Now the next one, I can now use the sum and difference law for this one here. So I can write limit as x approaches 3 of x cubed plus limit x approaches 3 of 2x minus limit x approaches 3 of 8, and everything is inside the square root, divided by here I can use the constant multiple law. So I can write 2 times limit x approaches 3 of x minus limit x approaches 3 of 5. Now let's go ahead and evaluate this. So now the first one here I can use, for this one I can use the, for this one I can use the power function law that we just got in the previous slide. For this one I can use the constant multiple and then this limit. So I can use limit as x approaches a of x equals a. And then for this one, the next one here, I can use the limit of constant function, which is constant itself. So same thing here. Here I can use this law, okay? For this one, I can use the constant law. So now we can go ahead and evaluate this limit. So the first one, if I use the power law, I can just plug that 3 in for x, and I can write 3 cubed plus, for this one, it's 2 times, and I can plug in 3, minus this is just 8, and everything is inside the square root, divided by, same thing here, 2 times, I can plug in 3, minus that limit is 5. Now let's go ahead and write it right here. So this is a square root of, so 3 squared is 3 cubed is 27, plus 2 times 3 is 6, 27 plus 6 minus 8, so the whole thing is 25, divided by, the bottom one is 6 minus 5, which is 1, and that gives us 5. Later on, I just show you how we can use all these rules, but we can do this in 1 or 2 steps, okay? We don't have to show all of this work, but I showed you all of this work just to show you how those limit laws apply here in a problem, okay? But later on, we can just do this in 2 steps. We can skip everything and we can jump from here right down here, okay? So now here is the big, really important rule that we have. Now the first one says for a polynomial function, so if our function is a polynomial function, then the limit as x approaches a of f of x equals to the value of the function. And it's very clear. So if you look at the graph of polynomial function, which has no breaks, no holes, nothing. So if you choose a point, if you choose a somewhere here, then as x approaches a, the corresponding value of the function is the limit, okay? So so if you have a polynomial function, you know a function is a polynomial function, then if you're finding the limit, then what you can do is you can just do substitution. Okay, you can find the value of the function and that gives you the limit. So it's super easy with the polynomial function. That comes from what we did with the limit laws. Okay, so if we break down just like the example that I did in the previous slide, so for any polynomial function, if you keep breaking that, use the sum and difference rule, use the constant multiple rule and use the power rule, then we'll get that. But now with this theorem, with this definition, we don't have to do all of those breaking down. If it is a polynomial function, just go ahead and substitute x with a, that gives you the limit. Okay, and that is true for a rational function as well. So if we have a rational function, we can go ahead and do a substitution as long as the denominator is not zero. If the denominator is zero, then we cannot do direct substitution, and that one we'll talk in the next video. Okay, so limit of a rational function and limit of a polynomial function and a rational function, we can just do substitution. Okay, we can just plug it in. For the rational one, just be careful. If you get zero in the denominator, we cannot do a direct substitution. Otherwise, we can do the direct substitution. So let's look at an example here. Now, the first one is a polynomial function. So as per the definition or the theorem that we just looked at, so what we can do is for a polynomial function, we can just do a direct substitution in order to evaluate the limit. So I'm going to do a direct substitution here. So this equals 2 times 2 cubed minus 3 times 2 squared plus 4 times 2 plus 5. Now, if you simplify this or put it into the calculator, we'll get 17. And that's the limit. See how easy this becomes? Now, if you have to draw the graph or make table, that would be a lot of work. But now, with this rule, we can evaluate the limit of a polynomial function so easily. Okay. Now here the next one is a rational function, and then for the rational function, what we have to do is we really have to be careful with the denominator. We can do a direct substitution as long as the denominator is not zero. So let's go ahead and check with the denominator first. Okay, so if I plug in 2 here, I get 2 squared, which is 4 minus 2, and that does not give me a 0. That means we can do a direct substitution here. So I can replace x with a. Here a is 2. So let's go ahead and do that. So I can write 2 to the 4th plus 5 times 2 minus 2 divided by 2 squared minus 2, and that gives us, so if you put it into your calculator, so this 16 plus 10 minus 2, and then 4 minus 2 is 2, and then you will get 24 over 2, and that gives us 12. So for any polynomial or rational function, we can do a direct substitution to find the limit. For a rational function, we just have to check the denominator. If we get a 0, then we cannot do a direct substitution. Now let's look at another example here. Now this is try problem. So I want you to pause the video, try to do it by yourself, and then resume the video and check the work. So for this problem, we have to be careful with two things. One thing, this denominator, the whole thing cannot be 0. That is for the rational function. And then we have a square root. So another thing that we need to be careful here with is when I plug that 7 in, I should not get a negative number inside these two square roots. So that's what I'm going to check first. So when I plug in 7, okay, so when I plug in 7 here, 7 minus 3 is 4, so positive 4. I'm not going to get a 0. That's good. So when I plug in 7 here, I get 7 plus 2, which is 9. So it's not a negative number. That's good. Now, when I take the square root of that, I get 3 minus 1. So the whole thing is not 0. So that means it's satisfying all the conditions for direct substitution, okay? So we are not getting negative under the square root, and then we are not getting 0 in the denominator. That means I can do a direct substitution here. So let's go ahead and do that. So when we do the direct substitution, so that becomes square root of 7 minus 3 plus 1 divided by square root of 7 plus 2 minus 1. 7 minus 3 is 4, square root of 4 is 2, so you get 2 plus 1 divided by square root of 9 is 3 minus 1 is 2. and then that gives us, okay, and then that gives us uh, 3 over 2. Okay, so let's look at another example. So we can use this limit laws for one-sided limit as well. Um, so let's go ahead and check that. Okay, so here we have a piecewise function. Okay, now you really have to have a good concept and understanding of what a piecewise function is. Okay, piecewise defined function. So now when you look over here, this function f of x equals 3x minus 1 if x is less than or equals to 1, and f of x equals square root of 2x minus 2 if x is greater than 1. So that means when we look at the domain of this function, so domain means the x value. So when we look at the x value, this is divided into two intervals. Okay, so at 1, from left of the 1, okay, so this one says x is less than or equals to 1. That means when the x values are over here, including 1 itself. So that is the domain of the first piece. So if the x value is 1 or less than 1, okay, including 1, if we have that, if our x values are here, including 1, then we'll use this definition of the function. Similarly, if x values are greater than 1, so if they are greater than 1, so in this one, 1 is not included. If we have 1, then we have to use the first piece, okay? So if the x values are greater than 1, then we are going to use the second piece of the function. So if x values are right here, okay, greater than 1, then we'll use this second piece of the function. So this is very important that you understand the piecewise function, okay? Now let's go ahead and evaluate the first limit. So it says limit of f of x as x approaches 1 from the left. That means here we are approaching to 1 from the left. That means our x values are over here, okay? So in that case, we have to use the first piece of the function. So this equals limit as x approaches 1 from the left of 3x minus 1. And this is a polynomial function, so we can just plug it in. So 3 times 1, so when I plug in 1, so I get 3 times 1 minus 1, so 3 times 1 minus 1, which gives us 2. Now the second part of that question is asking us to find the limit as x approaches 1 from the right of f of x. So that means this one, x values are right here. So we are approaching to 1 from the right. That means our x values are over here. So we'll be using the second piece of the function, okay? So we'll use the second definition of the function. So that means this equals limit as x approaches 1 from the right of square root of 2x minus 2. So you really have to be careful here with this square root, okay? Remember, we cannot have a negative inside the square root. And then this is very important that, so here in this case, so let me explain this, okay? Here, x is, so it is 1 here. We are approaching to 1 from the right. That means, so we have square root of 2x minus 2. So for example, here when we are approaching to 1 from the right, the x values are greater than 1. So remember, when we are finding limit, is not, we're not taking 1, we're not taking a when limit x approaches a. We are approaching from left and right. In this case, we are approaching from right. That means the x values are greater than 1. Okay, so x values are greater than 1. That means 2 times a number which is greater than 1 gives you a number which is greater than 2. So that means this number here, this 2x is it's really small number. I mean, it's close to 2, but it's still greater than 2 minus 2. So that means the whole thing is not going to give us negative number. The same limit, if this was limit x approaches 1 from the left, then we won't be able to plug it in and find the limit, because if that was the case, When we are approaching to 1 from the left, the x value is less than 1. Okay, it's very close to 1, but it's less than 1. So in that case, if we plug in that value in place of x, then 2 times a number which is smaller than 1 would give you a number less than 2. Then that 2x would be less than 2. So if you are subtracting 2 from a number less than 2, that would give you a negative number. That means if this limit was approaching from left, then we won't be able to evaluate the limit by direct substitution here, or we won't be able to evaluate that limit. But in this case, we are approaching from right. That means we are not going to get a negative number, so we can do the direct substitution here. So it's very important that you really understand this small thing here, okay? It looks simple, but this is really important, and you might run into problem if you really don't analyze that correctly, okay? So that means here we can just plug it in. So that means 2 times 1 is 2 minus 2, and that gives us 0. Now we saw that, okay, here the left hand limit is 2, the right hand limit is 0. That means this limit does not exist because the left hand limit is not same as right hand limit. Let's look at another example. So this is try now problem again. So that means you are going to try this on your own, and then you can check the work after you are done. Okay, so pause the video, try the problem, and then check the work. So here again, we have this number line. Now -1 is the one that divides the interval into two parts. So the first one says x is less than or equals -1. So we are over here. The left of -1, so x values are here. So that means for that, we are going to use this piece of the function. So when we are approaching to -1 from the left, we are going to use the first piece of function. So this limit equals limit x approaches -1 from the left of x squared plus 1. Again, this is a polynomial function, so we don't have a problem just plugging it in. So we'll do this direct substitution here. So when I substitute x with -1, so -1 is squared is 1 plus 1, so I'll get 2. Now when we're approaching to -1 from the right, okay, so it is this case here. So we are approaching to -1 from the right, which means we are using this interval or this piece of the function. Okay, so this equals limit x approaches -1 from the right of square root of x plus 1. Now again, you have to check here. So we are approaching to 1 from the right. Sorry, we are approaching to -1 from the right. That means x value is greater than -1. Okay, so that means this x is greater than -1. That means it's not going to give us a negative value here. That means we can do the direct substitution. So that gives us -1 plus 1, and that is 0. So the right hand limit is 0. So we have the left hand limit 2, right hand limit 0. They are not equal. That means this limit does not exist. So we'll just do this much for this video. Now in the next video, we'll look at a rational function where the denominator is 0. So far we just talked about the rational function where the denominator was not 0. But in the next video, we'll see what happens if the denominator is 0. How do we evaluate that function? So that's what we are going to do in the next video. For this video, we'll just stop right here.